Alright, so let's continue our discussions on the physics of the semiconductor, in this case silicon. So we just discussed the bond model, which you have seen that we consider the silicon as the crystal structure, and then each silicon has 4 bonds. And then we talk about the bond breaking to give you additional free electron, or we dope the silicon, then you get additional electron. And in this lecture, we are going to look at the silicon from another perspective, called band model. We are going to look at more discussions why this is called a band. And this is a reference chapter in the textbook, and also the recorded lecture from Professor Asif Khan. Okay, so let's look at the band model. Because later, actually, we are going to use more often the band model to describe the silicon than the bond model we have seen before. And here we want to view the atoms, let's say using those orbitals. So here you have the nucleus, and then you have your orbitals of the atom. So let's look at the very simple atom, for example, hydrogen atom. Then different orbital actually carry different energy level for the electron. So the closer to the nucleus, the lower the energy level. So here we have different energy level. So this n equals to 1, n equals to n equals to 3 is different energy level. This is discrete energy level in an atom. Of course, in the atom, the electrons tend to occupy lower levels first in equilibrium states. Of course, if you have some stimulus from outside, for example, laser or whatever, the electrons tend to move to the higher level, higher energy level. But in the equilibrium state, then electrons tend to occupy lower level first, lower energy level first. Okay, so then what happens when you bring individual atoms closer together to form a solid? So what we have seen in the previous slide is individual atom. You have the individual atom, the orbitals. And here the question is we are dealing with a piece of silicon. It's a solid. It's not an individual atom. So then the question is, if you bring those individual atoms together, close to each other, and form this crystal structure, then the energy band will change. Previously, the energy band here, or let's say in the energy diagram for individual atoms, are some discrete levels for the orbitals. So when we bring these atoms together to form a solid, then the energy level will change. Okay. We need to understand this from a simple example. Hopefully you have learned this before in some basic chemistry classes in your high school. So hydrogen molecule, H2, very simple, right? 2 hydrogen atoms, as shown there. Hydrogen, the first element, you have proton and the first orbital, 1s, which 1 electron occupies there. So you have 2 individual atoms, that's fine. But what happens to form a molecule is that you have to bring those 2 atoms close to each other so they can have some interaction. So once you bring those 2 atoms together, it will form this covalent bond. And there is a energy level splitting happens here. So those 2 1s orbital will split the energy level to be a lower energy level and higher energy level. And the lower energy level is the bonding level, and the higher energy level is anti-bonding level. And those 2 electrons will occupy which level? Any idea? Right? Lower level, as I said, always in the equilibrium state, any material system, the electrons tend to occupy lower energy level first. So this is what happened. Here, this arrow means 1 electron. And here we are looking at the energy levels of the electron. So here, this y-axis is the electron energy. So they used to be the same energy, because both of them are 1s orbital for individual atom. As you bring them together, then you split the energy level into the bonding and anti-bonding level. And these 2 electrons will occupy the lower level first. And then this is the covalent bond. So here we are looking at this through the energy level point of view. And we want to call this as a band model. Previously we looked at the bond. Now we look at the energy level of this, and we want to create band model, as you can see in the next. A few more words. I don't want to go into the too deep into this. When those 2 electrons form this bond, they are going to change the spin state. One is spin up, one is spin down. I don't want to go into the too deep into this. This is due to the Pauli exclusion principle in the quantum mechanics. So one energy level, you can only have 2 electrons. One is spin up, one is spin down. This is related to the magnetic property of the electrons. So I will skip those discussions, which is not very important for us. So then you have your hydrogen molecule here. Those 2 electrons somehow bonded together. Okay, so this is a simple example. Any questions? Now we need to look at the silicon. Okay. So silicon, we can also have this kind of energy diagram. And we look at the most outside 3s and 3p orbitals. Of course, there are some lower levels like 1s, 2s, 2p. But those are the core electrons. They don't move. So what I'm moving here is the 3s and 3p, and those 4 electrons. So of course, you will occupy 3s first. 3s first, one spin up and one spin down. So you have 2 electrons there, fill the 3s first, and then 3p. 3p, you have 3 slots there, and then you will have those 2 spin up occupied first. So if we think about the silicon solid with n number of silicon atoms, so we have n number of silicon atoms. So here, of course, we will have 2 n available states. So here we call it a state. That is a state where you can fill in the electron, or electron can occupy. So then 3s, 2 states, and we have an n number of atoms. So in total we have 2n available states. And then similarly here 6n available states for the 3p orbital. So this is the total system. And then the total number of electrons will be 4n. Each silicon will contribute 4 most outside shell electron. So it's 4n in total. And you can see here, in total we have 8n available states and 4n electrons. So those 4n electrons will somehow occupy part of those 8, a portion of those 8n states. So then, again, this is the question. When we bring this together, what will happen? So what will happen is like this, okay, conceptually. So individual silicon atom, we see those 3s and 3p. Those are individual discrete energy level. That means those atoms are far away from each other. Each look identical. So as now we bring them together, that means we are going to shrink the spacing between the atoms. So the interaction will happen. So we form this bond. But from the energy point of view, actually we are going to split the discrete energy level into a band. Okay. So this is how we introduce the model of band. And we are going to split this 3s and 3p into two bands. One is, this is as you bring the atoms closer to the silicon lattice spacing, that is the crystal structure we have seen earlier. So if at this distance, then we are going to create two bands. This is similar as the hydrogen case, right? You two hydrogen, when you make them together, then you have to split that energy level into this bonding and anti-bonding. This is similar stuff. We are going to split, but since here you have n number of the atom, then you are going to have many energy level. Unlike hydrogen, you have two hydrogen molecule only have two atoms, so you have two states. Here you have many states, the number of n, so you create a band. That is those two bands here. This is one band, this is another band. And here in the lower band, it will have 4n states. And in the upper band, it will have another 4n states. At the beginning, you have 8n states in total. So you split that. And then in total, you have 4n number of electrons. So those 4n number of electrons will tend to occupy the lower energy level. So this will be filled or occupied. So the electrons will tend to occupy the lower band first. So this is the concept of the band. I know it's a little not straightforward, but this is how we look at the silicon material from the band perspective. Any question? Okay, remember the band is respect to the energy level. So we are looking at the material from the electron energy point of view. So from the energy point of view, we just see those two bands separately. So the lower band and the upper band, those are the possible states for electrons to occupy. And here the argument is again, we look at this condition. Temperature equals to 0 Kelvin. We have seen this before in the bond model. We say that all the bonds are satisfied. There's no breaking of the bond. So no free electron. So in this band model, it's similar stuff. So at T equals to 0 Kelvin, all the electrons are in the lower band. So the lower band is fully filled here. And the upper band is fully empty. So no current flow. Why? Because the field states here, if you have electrons from this location to the other location, then that means here there's electron from here to here. Because it's fully filled, right? So you move to exchange two atoms, exchange two electrons. There's no net current. So that's why at this T equals to 0 K, there's no current. So two physical picture, but we are talking about the same phenomenon. Then let's look at the T larger than 0 Kelvin. So in this band picture, what happens is some electrons will have some thermal energy. to overcome the band gap. There's a gap between those two bands. And if the electron have enough thermal energy, it can jump from the filled state to the empty states. And once it jumps to the empty states, it will become the free electron because it can move. It's empty, so it can move anywhere, depending on the field, electric field. And what is left behind is the hole. So that's why you have the electron flow at finite temperature. That's why we have this electron hole. So once the electron jump from the filled states to the empty states, then you create a pair of electron and hole, and then you can have the current. But as we discussed before, this probability is so low, right? From the bond model, 1 out of 10 to the power 13 bonds will break. That means the probability for this electron jump from the filled state to the empty state is also very low, even at room temperature. But this is another way to look at this problem. So once you create the electron and hole pair, then you can have some current flow. So any questions here? Okay, I think we can end up